Hello everyone, welcome back. We have been discussing about the governing equations. We discussed the equations for the incompressible flow, compressible flows, and then we also discussed the dimensional form as well as non-dimensional form. Okay. So, now it is time to basically start solving those equations numerically. But before we solve these equations, we need to basically identify the nature of these equations: mass conservation equation, momentum conservation equation, and energy conservation equation. What do you mean by I mean by nature? So, as we have been discussing that for the incompressible flow, for example, if you have any disturbance that propagates immediately. Why? Why? Because the speed of sound is infinity, right. But on the other hand, when the flow is compressible, it travels with a finite speed, right. So, when you want to solve flows in different regimes, your equations behave differently. Okay. The character of the equation is different in different flow regimes. We have got the time dependent term, we have got the advection term, which is basically the transport term, we have got the shear stress term. So, the transport term, the advection term has got the velocity component. So, it travels based on the magnitude and the direction of the velocity. On the other hand, the shear stress term or the any viscous stress term would basically dissipate the heat in every direction, right. So, there is no directionality in your stress term, right. So, that has got a different character, that term has got a different character, right. Similarly, you have the pressure gradient term. It is very important to first understand how to basically numerically discretize each and every term in the Navier-Stokes equations, right. Only then we can finalize our numerical scheme that can be adopted to solve this kind of problems, and then we will be able to basically get a solution which is accurate as well as converged. Okay. So, before we get into this, we need to see some model equations, right. Some of the equations you might have already studied in your basic mathematics course, for example, the heat equation and the wave equation and so on and so forth, right. Some of the equations are the ordinary differential equations, partial differential equations, etc., right. So, if you compare certain terms of the Navier-Stokes equations, they may look similar to what you have already studied. So, what we are going to do, we are going to look for some very basic model equations today, okay, and try to characterize them so that we can basically find the mapping into the Navier-Stokes equations. So, that is the goal, that we will classify the differential equation based on the basically what are the how many characteristics they have. I will come to the characteristic what does it mean in some time, but as you know that there are many ways of classifying a differential equation. First of all, it is PDE or ODE. Secondly, whether it is linear or non-linear or maybe the quasi-linear, semi-linear, right, and then you can have it is homogeneous or non-homogeneous, and finally, based on their physical character, we can have whether the equation is elliptic or hyperbolic or parabolic. It can be a mix of all three also, okay, or in certain regimes it may display one character more strongly than the other, right. So, let us start with first just seeing the Navier-Stokes equation, right. So, for convenience I have used only the incompressible Navier-Stokes equation, but the discussion today does not depend on what is incompressible or compressible. What we are trying to see that what does each term indicate, right, whether what character they basically show, right. So, if you look at all these equations, the mass conservation, momentum conservation and energy conservation also, they can be basically written in a very simple form, okay, which is shown as below, right. So, here what I have done, I have taken this temporal term and the convection term, and this is the diffusion term, which can be viscous diffusion, and there is a source term, right. Now, if you put phi equal to 1, right, in this equation, right, and then let us put the diffusion term as equal to 0. This is your diffusion term, put 0 and source term equal to 0, right. So, what you will get del rho by del t plus del by del x I rho u I equal to 0, or in the vector form del rho by del t plus del dot rho u equal to 0. What is this? This is our mass conservation equation, and we can go to the incompressible limit, but let us not go there, we have already discussed that point. Now, you put phi equal to u here, right. So, now what you are going to do? We are going to put phi equal to u, okay, and gamma is equal to put mu, okay. So, we are putting phi equal to u and gamma is equal to mu, right. So, how will this equation look like? Del rho u by del t plus del, let us write in the vector form only, okay, so that it is convenient for you. Rho u is equal to del dot gamma del rho and plus s, okay, which can be the source term, right. So, what is this? How does this equation look like? This is like your momentum conservation equation. I put u, you can put v and w, and you can get the equation for the y momentum and g momentum, okay. So, this is your x momentum equation, right. You can also in the source term, you can also put the body forces also, right. If you replace phi equal to E, okay, replace phi by E now, then what you will get? You will get the energy conservation, okay. How will you do that? The del by del t rho E plus del dot rho u E, and see I have not put the pressure gradient term, but that can be absorbed here in phi, okay. So, here you can have like we have discussed that because you will have del p by del x I, which can be written as delta I j, delta p by del x j, and on the left side you have del by del x j rho u by u j, right. So, you can basically club them together, right. So, this will become del dot rho u e is equal to del dot gamma e, okay, and this is your the work done due to stress, okay, and plus the source term. The source term of course will vary between your energy conservation, mass conservation and momentum conservation. So, all the equations can be represented in the single form, which has got some temporal term, time dependent term, which shows the change in the quantity, the rate of change of quantity, then the transport, okay, the transfer of the quantity from one point to another point, okay, and then you have the diffusion due to the viscous forces, okay, the stress that gets developed, and finally, you can have some source term, right. Now, let us look at very simple equations, okay, and then we will basically combine all these simple equations that you already know to see how this they can be represented in this form, okay. You might have already heard that the Navier-Stokes equations are nonlinear equations, okay, and then they are basically nonlinear equations, okay, non-homogeneous equations. It may be non-homogeneous equation if you have the source term present, okay. It is multidimensional. So, it is quite complicated expression. It has the it is a PDE because it has the time as well as space dependence. So, all those things are there, right. So, let us look at some simple equations in the beginning. So, I have put together two equations that you have, I am sure you must have studied in your math course. So, one is your heat equation, which is nothing but del T by del T, and if your thermal conductivity is constant, you are not considering the variation of the conductivity, you can take this in the one dimensional flow, you can take this k dt by dx square, right. So, let us say if you have a rod, okay, and if you heat it up on one side and see how the temperature is changing with time. So, you can use it, this is the unsteady heat conduction equation, right. And I will be using the short form at many times. So, this delta by dt can be written as T subscript T, okay. That means subscript indicates that this is the partial derivative with respect to time, then this is k, okay, and T x x, that means it is basically differentiate twice with respect to x, right. So, this is your unsteady heat conduction, okay. And if it is steady state heat conduction, then this T T T term goes away and what you have is T x x, okay, equal to 0, right, which is nothing but del to T by del x square is equal to 0, right. And this is a very well known form, well known equation that you know is the Laplacian equation. Okay, this is the form of a Laplacian equation. Right, the second equation that we have studied is the wave equation. Okay, suppose there is a string here, okay, and then you just perturb it, okay, at some initial condition, the string will vibrate and the waves will travel. So, we will be solving this problem using the wave equation, and the wave equation is given as delta u, and u is some initial disturbance, some function, okay, you can write phi also, c square del to u by del x square, but here the c plays a very important role. Okay, unlike in the heat equation where the information travels at an infinite speed. So, here the information travel at an infinite speed, okay. Here it travels at a finite speed, okay, which is given by c here, right. So, for example, let us say you put a delta function or a point source, let us say in this room I put a point source somewhere, let me first consider the heat equation, put a heat source, okay, immediately it will work in a way that it will be distributed everywhere at an infinite speed, and it will reach to an equilibrium to give basically a solution, right, which does not have any discontinuity. Right. On the other hand, if you have if I am speaking here, I am speaking to you, the sound is travelling and it is travelling at a constant speed, which is the speed of sound, okay, which can be determined based on the room temperature, and we have talked about this c equal to square root of gamma r t for the isentropic process, right, which is fairly valid because we are not adding heat when we are speaking, right. So, isentropic process can be assumed, right. So, the sound basically travels. So, if I put a delta function, let us say I speak and then I stop speaking, it will take some time for the sound to reach to you, and if further you are, it will basically take more time to reach there, okay, because it is travelling at a finite speed. Okay. Now, for the delta function, let us say if I start with a delta function. So, my u is equal to delta x, okay, for the wave equation, and similarly that is a point source, I am giving point source in the wave equation. Similarly, I can give the point source in the heat equation also, and if you solve those equations analytically, which is presented in the last slide, okay. So, the solution will look very different, okay. So, this is the solution that you will find out for the heat equation. Without going into the derivations, I am sure you must have derived it in your math course. You know how to solve the partial differential equations, okay, finding the general solution on particular integral, and you can basically solve it, okay. So, you can see that there is a sum which is exponential minus x squared power 4t, okay. So, even if at a very small t, okay, it will decay very fast, okay, and basically it will dissipate everywhere, okay, it will distribute everywhere in a very small time, and that is why we say that it happens at an infinite speed. On the other hand, if you try to solve for the wave equation for the same delta function disturbance, okay, the initial disturbance at t equal to 0, your solution will look something like this. half x minus c t and half x delta x plus c t and half delta x minus c t, which means that there is c which is the speed of sound, okay, and which has got both plus c and minus c, okay, the sum on the front and sum on the back, okay, and you can see that it depends both x and t, okay, and it will be only be valid when x minus because it is a delta function, right. So, it will be only valid at a point which is x minus c t or x plus c t, right. So, you will have so we will have wave travelling, you will feel the presence of the wave at x minus c t, then there is no wave, then again there is a wave, presence of the wave is felt, and so on and so forth, right. So, that is how your sound wave equation presents the solution for a delta function, right. So, the other equation that you know is the boundary layer equation. So, if there is a flat plate, okay, I am just looking at some of the equations that you already know in your heat transfer and fluid mechanics course, right. So, if the flow is happening from the left and this is the edge of the plate, so the boundary layer will start developing, and if you have read about the boundary layer theory, right. So, the boundary layer theory describes the development of the boundary layer provided the condition that your delta is much smaller than L. So, if this is distance is L and this distance is delta, okay. So, the boundary layer theory tells you how this delta will evolve but in the space, right. You can see that as the L is changing, your delta will change, right. And for the flat plate, you have all kind of assumptions. One is that del p by del y equal to 0, right. So, there is no variation of pressure in the boundary layer. So, if I fix my coordinate system, this is my x and this is my y, okay. So, del p by del y equal to 0, and similarly del to u by del x square is smaller than del to u by del y square. So, you and we have already derived the Navier-Stokes equation. So, there are some conditions, it is a steady state, okay, and the condition is it is incompressible, and there are few more, okay, and finally, you come to this equation which is the boundary layer equation, right. We will look at the character of this boundary layer equation also. So, the boundary layer equation describes the flow, it basically it is the ratio of the viscous force and the inertial force is the balance between these two forces. So, if the Reynolds number is very high, then the role of the viscous force is limited to very small area. So, if the boundary layer Reynolds number is quite high, then you will have the boundary layer which is very close to this region. Although you will have the gradient, you have to have the boundary layer, you cannot ignore the boundary layer, okay, even no matter how high your initial force is, okay, you will have the gradient changing, you will have the velocity going to 0 here and velocity going to u infinity here, okay, but this distance may become very small, the delta may become very small, but delta has to be there, okay. So, we will look at the nature of this equation also when we go to the classification of the PDEs. Okay, right now I am just describing what are the equations that you already know. Okay, one is the linear convection equation and it is actually another form of the wave equation that we already saw. Okay. So, linear convection equation, there is a big role of linear convection equation in the development of different schemes which are currently used in CFD. So, basically two schemes, one is the convection scheme, okay, and another is the diffusion scheme. Okay. So, these two basically this relates to the wave and this relates to the heat. Okay. So, these two equations have played a big role in devising schemes which can be used for the Navier-Stokes equations, because your the viscous term basically is similar, I mean it emulates the diffusion process, and your advection term, because you have the du by dx partial u by partial x is there. So, that is the advection term is dictated by the convection equation, although it is a non-linear convection, but the non-linear convection, right. So, how it is related to the wave equation? So, if you just take a derivative of with respect to let us say time here, so you can write this del u by del t equal to minus c del u by del x, right. So, you can take a derivative with respect to time again, okay, that will become minus C del to u by del x del t, right. And then what you do, you can basically interchange the derivatives to become C del by del x, and this is del by del t, right. And this del u by del t is nothing but minus C del u by del x, right. So, minus C del by del x minus C del u by del x, right, which is nothing but C square del to u by del x square. So, del to u by del t square is equal to C square del to u by del x square. Okay. So, this is the first order and this is the second order, but both represent the wave equation, okay, or basically the propagation of wave in a medium. Okay. So, now that we have some we just reviewed some of the equations that we have already studied or gone through in our math course or even in the fluid dynamics course, let us look at how to classify these PDEs. Okay. So, first of all we need to find out, I mean there are some very basic whether it is a PDE or ODE, right. So, and then we will see whether it is linear or non-linear, then it is homogeneous or non-homogeneous, and finally, we will go to a little bit more advanced topic, which is whether the equation can be called a elliptic, parabolic or hyperbolic, and it has got a physical significance. That is why we will spend some time on this characterization. Okay. So, before going into the ODE, PDE or even other things, let us have some basics. First is the order of the differential equation. So, the order of the differential equation is basically defined to be that of the highest order derivative it contains. So, let us say if you have a function del to q by del x q plus u del to u by del x square and plus u equal to 0, something like that. Okay. So, the order of this is your 3, yeah, this is the third order differential equation, right. And now, the degree of the differential equation is defined as the power to which the highest order derivative is raised. So, remember this highest order derivative is very important when you are characterizing a PDE, right, and this will come to again and again, right. So, for example, in this if you see the degree is the 1, right. So, let us say if I raise this to as del to u by del x square to e square, right, still the degree remains 1. Why? Because the power to the highest order derivative is 1, right. Its degree will change only when we have this del t q by del x q, if I change the degree of this, right, the power of this, otherwise the degree will not change. Okay. So, this now its order is 3 and degree is 2, right. So, we learnt about the order and the degree. Okay. And now about PDE and ODE. So, let us define this independent and dependent variables. Okay. So, for example, if you look at the Navier-Stokes equations, okay, so del rho u by del t plus del by del x j rho u I u j equal to minus del p by del x j plus del by del x j tau I j, okay, or you can write in terms of velocity gradient there. Okay, tau I j can be written in terms of velocity gradient, right. So, here you can see what are the independent variables you have t. So, the independent variables you have are basically t and x j, which are basically x, y and g if it is a 3-dimensional flow, right. And what are the dependent variables? Of course, you know, okay, rho, u, v, p and all those things. Okay, these are basically your dependent variables. These are the dependent variables. Okay. So, if a equation has just one independent variable, that means for example, it is a 1D steady state flow. Okay. Let us say it is a steady state 1D flow, right. Then what will happen? The t will disappear. Okay, the t, y, z all disappears. Okay. And then what is the independent variable that we have is only x. Okay. In that case it will become an ODE, right. So, if it becomes an ODE, you have many advantages, as you already know, it becomes very easy to solve, but unfortunately most of the cases, most of the realistic cases that we come across in our fluid dynamics are basically the cases where it depends on more than one spatial direction as well as on time, right. So, the Navier-Stokes equations are basically the partial differential equations, right, and it is called spatio-temporal PDE because it depends on space as well as it depends on time. So, PDE when the independent variables are more than one, well, okay, here it is x, y, z and t, but it can be anything which comes at the denominator in derivative, they are basically the independent variables, right, and in the numerator they are the dependent variable which are depending on those independent variables, right. So, for example, here rho can be expressed as rho x, y, z and t. So, rho depends on all x, y, z and t. So, rho is the dependent variable and x, y, z, t becomes the independent variable. Okay. Now, let us look at the different nature of the PDEs. Okay. So, we will start with typically in the literature we have linear and non-linear, okay, but then you have some sub classification of the non-linear process which are basically the quasi linear or the semi linear. Okay. So, we will briefly go into the discussion of these quasi linear and semi linear equations. Okay. Although what I have seen is that in the literature they have basically mixed these two terminologies and they have different they may have different definitions on how you define the quasi linear process or the semi linear process, right, but the difference between the non-linear and linear is quite clear. Okay. So, the quasi linear is for example the derivatives of the highest order are linear. Okay. So, for example, if you take an example, so which is basically del to u by del x square, or just write this, yeah, okay, let me write here del to u by del y square plus del to u by del z square is equal to 0, right. So, if you look at this expression, okay, so what are the derivatives of the highest order? Okay. So, these are here they are all of the same order, but you can have other terms also. So, if they are linear, then it is a quasi linear thing. So, okay, this is a quasi linear process, right. You can have other expressions also. Let me write some other expressions. Okay, let us say I have expression which is u x x x plus x square u y y y plus u square, okay, u t t equal to 0, right. So, here you can, as you can see, here the order was 2, okay, here the order is 3, okay, and this is also a equation of the quasi linear. Okay. But let us take an example which is basically u x y square and plus u x plus u y equal to 0. Let us take this. So, here the derivative of the what is the highest order? The order is 2 and the derivative of the highest order is basically not linear, this is u x y square. So, this is not quasi linear. So, this is not quasi linear. Okay. These two are quasi linear, but this is not the quasi linear. Okay. Within the quasi linear we can have more basically classifications. So, one is the semi linear, which is that it should be quasi linear, and second is that coefficients of the highest derivative, okay, should not contain either dependent variable or its derivative, right. So, let me give you one example which is basically quasi linear, but not semi linear. Okay. So, this is by default your semi linear, right, it is quasi linear and the coefficient of highest derivative does not contain any either dependent variable or its derivative. Okay. But if you look at this example, okay, this is neither quasi linear, this is neither semi linear, because the precondition for semi linearity is that it should be quasi linear. So, if it is not quasi linear, it cannot be semi linear. But let me take you for one example which is basically quasi linear, but not semi linear. Okay. So, that example could be, let us say u t t plus u x t okay, is equal to something, okay, let us say x square. Okay. So, this you can see that derivatives of the highest order are linear. Okay. So, this is quasi linear, okay, but this is not semi linear. Okay. So, this is very important to know that this is not semi linear, because it should not contain the either dependent variable or its derivative. Here it contains the dependent variable, which is u. Okay. So, this is not semi linear, and if it is not quasi linear, okay, then it will be, it has to be the non-linear. Okay. So, I will give you just example. So, this is for example, this is a non-linear equation. Okay. This equation that we see is a non-linear equation. Okay. And for other classification that I can talk about, for example, this is a non-homogeneous equation, because there is an x square coming on the right side. So, what is the difference between homogeneous and non-homogeneous equation? So, in the non-homogeneous equation, so all the terms contain dependent variable or its derivative, right. It should not contain an independent variable. Here in this particular case, you have an independent variable coming x square. Okay. So, you can write an expression, I mean think of any expression, let us say if you are talking about the Poisson equation, okay, if let us say I write del square u is equal to x, okay, or y, whatever it is. So, this is your non-homogeneous equation, because it has an independent variable coming in the equation. The linear equations are very simple. Okay. It should not multiply, I mean the dependent variable and all its partial derivative must occur linearly, right. So, all, I mean the precondition it has to be quasi linear and it has to be semi linear, then only it can become linear, right, and it should not the derivative should not multiply any of this dependent variable, right, and then only it can become the linear equation. And I will give you some example. I mean we already saw many examples, for example, the heat equation or the linear convection equation, they all these equations that we saw. So, this is let us say u t equal to c u x, okay, minus c u x. Okay. This is your linear equation, but if I just replace, let me write in the form that we already wrote, plus c u x equal to 0. So, this is your linear equation, and if I just write it u t plus u u x equal to 0. So, this is a linear equation, but here the dependent variable and its partial. So, this is the partial derivative, okay, it is not occurring linearly. Okay. So, then this is becomes a non-linear equation, okay, because the derivative u x. So, in this particular case your wave is travelling the speed of sound c, right. Here if you want to solve this equation, it is travelling at a speed of sound, the speed which is u, and that u has to be determined from the equation, right. So, it is non-linear depending. In other way you can see, if you write this expression u t plus u u x equal to 0, okay. So, this is del u by del t plus u del u by del x equal to 0, right. So, this is del u by del t, and you can write del by del x u square by 2 equal to 0, right. So, this is occurring non-linearly, right, you can clearly see here. So, that is why this is a non-linear equation, this is non-linear PDE and this is homogeneous. Okay. So, in this particular class we basically reviewed some of our basic ideas of the linear equation, non-linear equation, homogeneous equation, non-homogeneous equation, and then what are the PDEs and ODEs. In the next class what we will do, we will go to further classification and we will see the equations, how we can classify these equations as whether they are elliptic, parabolic or hyperbolic, and what does it mean. Okay. So, with that we will stop today and we will continue our discussion in the next class. Thank you very much.